Hello, everyone. I'm Steve Chrismer, newly retired from Amtrak. Let me bring up my presentation. And I'm going to talk to you today on the subject of track substructure design methodologies in connection with the theme of the workshop, which is track substructure challenges. When we talk about challenges to us, it's useful to think back over recent decades and how we approached challenges over that time. And of course, the issue then was, back about 40 years ago, and pretty much in the decade of the 80s, the challenge being that of heavy axle loads. The coming of 110-ton cars and 125-ton cars, up from 100-ton. And of course, at the time, only 10 years before that, around 1970, the industry was struggling with the increase from 70-ton to 100-ton. And to put it bluntly, the industry was not ready for that change. So by the time the 1980s rolled around and we knew that heavy axle loads were coming once again, there was a big movement to get ready for that and really be not caught off guard. We did such things as improved strength of materials. We developed more durable track maintenance methods, all in service of accommodating heavier axle loads. So that is something where we prevailed, I think. It's fair to say that we did pretty well. And we're living with the benefits of that now. The question then is, well, what is the next challenge to come along? How can we meet that? And I think it's fair to say that the climate crisis provides an opportunity, because associated with that, you can see a declining demand of the hauling of carbon, specifically crude oil and coal. And as that is phased out and decreased year to year, we can, in response, shift to higher value, higher profit express freight to provide the growth the industry needs to be vital and grow into the future. A competitive express freight, though, the speed of that would require to be greater than Class 5. That's if we want to get goods off of the highway from the trucks and onto the rails. A competitive speed, again, would be in the Class 6 range. We can manage that, but we have to expect that this will produce increased impact wheel loads, something that we must then, of course, manage. But we have the tools and the methods that we have already developed to cope with heavy axle load that can now be applied to the same challenge that would be issued, that of not necessarily increasing static wheel loads, but increased dynamic wheel loads, impact loading. So then the argument would be to build on the success that we've had in adapting track to heavy axle load to now adapt the track to higher speed freight. And as I mentioned, we do have more durable track maintenance methods that we could apply to this that would certainly provide the benefit. We, in the course of adapting to higher speed freight, would need to increase track capacity, which means to some extent new track construction, but probably more so of upgrading existing track from, let's say, a Class 4 to a Class 6. To aid us in this regard, we can make use of, as I said, the design methods that have been developed, one of them being the granular layer thickness design method. And the granular layer is the ballast plus the subballast. The combined thickness of that over the subgrade soil, which tends to be soft and deformable, and which you want to protect by lowering the stress so you don't have excessive deformation. The GLT, or granular layer thickness method, is now well understood and practiced, and we can use that very successfully to prevent excessive subgrade deformation as a result. And the dynamic loading would definitely penetrate down to that level. So even though we're not talking about increased static axle loads or wheel loads, we are certainly talking about increased impact loads that have a penetrating effect into the substructure. We also have availability of such tools as the ground penetrating radar, or GPR. Now that tool allows us to effectively look into the track substructure well below the ballast surface, to find out what problems there are, what is the nature of the instability, if there is one, to locate them and to diagnose them, and then prescribe a remedial method. Now that's especially useful for upgrading existing track. Let's say if you have an existing class 4 track that you want to provide class 6 speeds, then the GPR could be applied well before you ever start running the express freight service, because it's usually more cost effective to fix things beforehand rather than have them become apparent under service of higher speeds. But how would we manage this in the sense of the track that these express freight would run on? How do we have sort of a shared use approach? As a guide, we can use the shared use approach between passenger and freight track. And I want to show you 3 scenarios here that are possible approaches to this very issue. The one on the left, shared track, is simply that both freight and higher speed passenger can occupy either track. That is done actually on the Northeast Corridor of Amtrak on a regular basis. And I think it's a feather in the cap of Amtrak engineers that they can manage this situation and do so very well. But it's not something that you might desire to do if you had your choice. The reason is that the freight loading produces more, or causes more track settlement and roughness, and therefore more increased maintenance, even more so than the difference in the wheel load, the wheel load of the freight compared to that of the lighter passenger train. So the damage is exponentially above that difference. We have to account for that. I'll show an example of that in just a second. Because of that fact, we might look at case 2 in shared right of way, where you have now the freight, the heavier axle load freight on one track and the passenger on another. So the passenger track might be class 6 or 7, the freight track might be class 4, and where the freight would go over to the passenger track would maybe be a rare move, an unusual move. Of course, you can't say it would never happen, but you want to limit that, because as I said, it does not take very much freight loading for that loading to dominate the track response, settlement, roughness, and then required maintenance, of course. So this would be a more desirable situation, and yet even probably more ideal is the case on the right. If this is possible, where you have now true separation between, let's say, the standard freight, nominal freight, and the heavy axle load, and the higher speed passenger, or in our case, the higher speed freight being on the tracks on the left. Again, that right-of-way width is, well, quite a challenge to us. We don't often have that available, but if we did, that's maybe you could hold out that as sort of the ultimate desirability. But realistically, you might have something in between cases 2 and 3. Let's say a case 2 with an occasional third track, not continuously, but over certain track lines. That would provide the extra capacity that you need to run both services. So we can take from this case of how we share between freight and passenger to consider how we would share track between heavy axle load freight or nominal standard freight and express freight, because they exist in 2 different speeds, and the wheel loads are obviously very different as well, static wheel loads. Here's an example of the problem of case 1, which you can run into. This is an actual example, again, from Amtrak's Northeast Corridor, where an investigation showed that there was quite a bit of subgrade shear and movement and a lot of track maintenance that occurred as a result of this. And you can use the analytical methods that we've developed to prove, in fact, that most of this, almost all of it, is due to the heavy axle load. If you just had the lighter loading of passenger track, you wouldn't see anything close to this. In fact, the students in my track engineering course at University of Delaware cannot get out of the class without being able to calculate this very thing. So this is predictable. We have the methods to show which loading scenario provides this kind of deformation. And we see this from excavations of the track as well to verify it. So this is what we'd like to avoid. Very hard to run higher speed track where the agenda for maintenance is set by the higher load of the freight. So if we can separate those two out, all the better for us. All right, well, what kind of wheel loads are we talking about and speeds of express freight? Here's a wheel impact load detector on Amtrak's Northeast Corridor with a strain gauge configuration to measure that very thing, the static load plus the dynamic augment or impact load on top of that. What sort of loads are we talking about with express freight? Well, let's discuss that. First, we'll handle the question, as I get to it there, of speed. The table on the right is the standard way of looking at track classes and the allowable speeds for the two different types of rail operations of freight and passenger, maximum authorized speed, or maximum allowable speed for those track classes. The graph on the left is related to that table, where it's showing you the allowable deviation, track deviation for a certain geometry parameter, the mid-chord offset over a 62-foot chord. You could pick another geometry parameter, but this is the one we've chosen because it illustrates the point. You see the maximum allowable deviation, of course, gets smaller with higher and higher track classes, but it does so in a very nonlinear fashion, and that's the point. If you were to upgrade the track from class 3 to class 4, there is a bit of tightening that you would do with the geometry and to be able to maintain that. But if you were to jump from a class 4 to a class 5, you see there is a nonlinear sort of increased effort that you would have to do. Again, just based on this one parameter, it's a first order approximation to how much work you'd have to supply to provide that track upgrade. Now, if we go to track class 5 to class 6, we notice, yes, it has to, it's a tighter yet requirement, but not quite as much as going from class 4 to class 5. Again, this is only meant as an approximate indicator, but it tells us that there are different levels of maintenance input, of upgrading effort that you would have to apply to go from a class 4 to class 5 to a class 6. So we are specifically talking about, if class 4 is your typical situation for a freight track, then upgrading to a class 6 would allow express freight to occur at a speed that is competitive with highway, with the transport of goods on the trucks on the highway. Class 5, now we're already doing this to some extent. When I say express freight, yes, there is track that has been upgraded to class 5 to allow somewhat express freight up around 70 miles an hour, maybe a little bit more. But we really have to, if we want to have true express freight, to break through that into class 6 speeds. Now the range of above 80 up to 110, the express freight would probably be on the lower end of that, not necessarily as high as 110, but perhaps 90 miles an hour. And the reason we say that is, when we look at it, what a competitive express freight speed would be, competitive with the trucking industry, we have to consider that a conventional 3-piece truck for freight cars is a workhorse and does very well. And if you maintain it well enough, yes, it will pass the stability requirements against hunting, according to the AAR Chapter 11 test, up to around 70 miles an hour, usually without a problem. As you try to approach 80 miles an hour, though, it often will not pass that test. And above 80, it's very difficult. And the reason is that even with the proper care and maintenance of a 3-piece truck, it simply was not designed for those higher speeds, and instability or hunting at those higher speeds, especially in the unloaded condition, is a concern. Therefore, if we want to compete with long-haul over-the-road trucks for these high-priority shipments, we would need to increase our average freight speed up to around 60 miles an hour. But doing so means that we have to increase the maximum train speed to something in the range of, as I mentioned, class 6 track of 90 to 110. But let's say 90 miles an hour. So clearly that requires a new type of freight truck from the conventional three-piece. And there has been work in that regard. Here's an example of one type of truck that has gone pretty far along the validation process. And you'll notice that it is rated at 70 tons. So, we're sort of going backward a little bit, giving up a bit on car capacity because we're going faster. This 70-ton truck with advanced design has been through a lot of analytical modeling and actual physical testing, and it has been validated for higher speed. And offhand, I'm not sure, maybe 110 miles an hour, even above, I think, was it tested as acceptable. But if we have such a design, if we can go 90 miles an hour, now we are in a competitive sort of situation with trucking, as I said. 70 ton, there is some thought that maybe we could have 100 ton at higher speed, but now that's even more of a challenge because the static wheel load is kind of fighting you, right? You're trying to minimize the impact load. So if you decrease the static wheel load down to what it would be for a 70-ton truck, you're really helping yourself. And here's how we can sort of decide that. Here's the well-known P2 force equation, which we can use to manage the situation so that impact loads don't get too large. This equation is quite complex, of course, but basically all it's saying is that the P2 force is a combination of the static load plus a dynamic augment on top of that, the impact load in addition to the static load here. Sometimes P2 force is thought to be only the impact load. It's actually both, the static load plus the impact load. And this rather complex part of the equation here is looking at that dynamic augment. It has a number of terms which we won't go into here, but you can read about it in the APTA standard that's under development that's mentioned there, where all terms are defined and there's example values for those input parameters. What it's doing is it's trying to assess what the impact load would be to a reference condition, say at a battered joint here or a dipped weld, where the angle is exaggerated just to show you. It might only be half a degree or a degree, not very many radians, and that would be in units of radians. So what you'd want to do is, for an increase, to give the green light to increased speed for express freight, you would have to manage or somehow maybe reduce the static wheel load in conjunction with reducing this parameter, m sub u. That's the unsprung mass. And notice that it's in this equation 4 times, and it actually is weighted pretty heavily as well as numerically in the equation. So the unsprung mass is nothing more than basically steel on steel where there's no resiliency. So that would be the wheel sets, right? The axle, any brake discs. This is all steel, metal with no resiliency, so it's unsprung. That can also include the bearings. That's part of the unsprung mass. And if it's a motorized truck, then you would include a portion of the gearbox as well, maybe something around half of the gearbox. The other half would be suspended off the truck. And typically the entire motor would be truck hung or maybe car body suspended. So you don't account for the truck in unsprung mass. But this says that you would want to, when you manage this from a vehicle point of view, you would want to decrease the unsprung mass as much as you could to keep dynamic wheel loads within an acceptable range for going at a higher speed for the freight. And if you can, to the extent you can, reduce the static wheel load to that point. So those two things can help you quite a bit. Increasing velocity means decreasing or keeping within check the static wheel load and the unsprung mass. And that's how we can manage this situation. Turning back to the track now, since we've delved into the vehicle maybe a little too much. These analytical methods that I spoke of, one of them being the granular layer thickness design method, can aid us by quite a bit to determine, especially if it's an existing track, we can determine if this thickness, the GLT, is sufficient for given the increased loading from express freight so that the subgrade settlement is not substantially increased, requiring a lot more maintenance. Also, you can use the GLT design method for if you have new track construction, then again, you want to come in with a design H value that limits, again, the amount of subgrade deformation. And these parameters, there's a few of them that you would have to know or have some idea of: the resilient modulus of the ballast and subballast, and that of the subgrade, the subgrade material strength, the soil type, and these dimensions: the thickness of the potentially deforming soft layer, and the thickness of the ballast and subballast, if it's an existing track. How would you obtain those values? Well, there is a one-stop shopping approach, and that is the cone penetrometer test here in a high-rail vehicle. With a cone, the instrumented cone would come out of this body and go into the track substructure at a slow rate, continuous rate, all the time you're measuring the cone tip resistance here and the resistance along the sleeve. And it plots something like this. That gives you an idea of the material strength of the subgrade. Actually, it gives you all of these parameters that are shown here so that you can then use this design approach. So we have these methods, they're available, and we can apply them to this situation. I'm drawing short on time, so let me just wrap this up by mentioning a couple of examples of increased durability maintenance methods, increased above from that of the conventional tamping. There's one I don't show here, and that is the stone blowing or stone injection, which requires a different type of machine entirely, or can be held handheld. But when you raise the tie, you blow in a certain amount of stone over top of the ballast that's already there. So you don't disturb the ballast. In other words, the track doesn't have a chance to settle back down because it's not disturbed. The ballast is not loosened by tamping. Rather, you add a little bit of stone on top of the existing stable stone that's there. That provides a much more durable and long-lasting effect, something like 3 or 4 or 5 times longer than you would get with conventional tamping. But as I say, that requires a new piece of equipment to do that. I want to focus on this other improved design or method that you could apply, which is design overlift tamping. Now that applies a conventional tamper, but in a modified, improved fashion, where you would come along and measure a pre-existing dip in the track, and you would calculate where the track should be based on the design profile, and then produce through the design method, the amount of overlift that you would apply along the track, because it's variable, to produce a track profile that will, once you resume running trains over it, would settle into this design profile that you see here. So that's a measured amount of overlift, variable based on how much residual lift you want. This has all been worked out, and it has been shown to be valid and durable under passenger loading and up to heavy axle load freight. Again, something like a order of 4 or 5 times longer increased durability over conventional tamping has been shown to be the case. Here's an example of that, where again you see the existing rough profile, and then just after you apply design overlift tamping, looks a little bit rough, not quite as smooth as you want it to be, but just wait, because when you start running trains, it does quickly settle into a more smooth profile. And in this case, after about a year of traffic, it is now about where you'd want it to be, and further degradation would take place very slowly. So it spends most of its time right around the optimum design profile. In effect, what you're doing is you're eliminating ballast memory. It doesn't sense where it used to be, so it doesn't try to go back to that. But conventional tamping, very often it does. Again, the increased durability of something, of methods such as this, can help us a lot, especially in regard to express freight, because it's all the more important not to have to get out there and get in the way of express freight, to get out on the track and do whatever you're doing and get out and not have to go back for a long time. That is the goal of this. Well, why do all of this? What is the impetus for this amount of change? As I said, I think it comes out of the climate crisis and how our industry has to adapt to that. The Union of Concerned Scientists, for example, issued a report, quote, that said to avoid the worst consequences of climate change, we'll need to reach net zero carbon emissions by 2050 or sooner. Parallel to that, the Intergovernmental Panel on Climate Change from 2018 set a target of 45% reduction in global emissions by 2030, which is not that far away, with the same purpose, to avoid the worst consequences, something that we can live with and manage. Fortunately, our industry starts with the benefits of inherent higher fuel efficiency and low rolling friction at the wheel-to-rail contact, which sets us ahead of the trucking industry right there. But we can use that and build upon it to mode shift then those goods, high value, higher profit goods from the highway to the rails, from the roads to the rails. And I mentioned passengers in there too, because, well, we haven't talked about economics, but it's a fair bet that public money would have to be involved in some way to increase track capacity to allow express freight. And the public would rightly desire to have, as a result of their investment, more regional passenger rail in addition to long distance passenger. So I end with a quote by an architect, Daniel Burnham, who was the architect of Amtrak's Union Station in Washington, D.C. Make no small plans, aim high and hope and work. We can do this. We have the tools, and we have done this sort of thing before in our profession. And if we do so, we can have an industry that will provide growth well into the future. So we are up to the challenge. We certainly can do this. And with that, I thank you, and I understand that there may be questions if I've allowed enough time for that. So thanks for your attention. I look forward to any questions.